The example I would like to show you now is called the three-door problem, and I got it from the first chapter in the book Probabilistic Robotics by Professor Sebastian Thrun, who is also the father of Stanley, the first ever self-driving car. So let's say that we have a corridor, and in this corridor I have a robot. Here is my robot. Now this robot has no idea where it is located inside the corridor. So if the robot has no idea where it is, we can describe this using a uniform distribution. And therefore, if I have some function called p of x or believe of x, where I have x here, and x is in fact the robot location in the corridor, then p of x or believe of x, if I don't know anything, should look like this. But in order to make this interesting, let us assume that in this corridor there are three doors. One door is at x equals 10, one door is at x equals 20, and one door is at x equals 80. Our robot, by the way, is located at x equals 10, but he doesn't know it, so don't tell him. Our robot has what is called a door sensor, meaning that when it is near a door, it knows. Why? Maybe the door is opened and there is a draft of air or more light. So if a robot has a door sensor and it senses that it is near a door, what will the current probability look like? Now pay attention. There are two things here. A, the robot knows that it is near a door. And the second thing, our algorithm knows the map, meaning our algorithm knows that we have door at point 10, 20, and 80. So if we think about it, we are supposed to get something like this. At point 10, 20, and 80, we have three peaks. Why? The doors are indistinguishable. I just sensed a door, but I cannot differ one door from the other. I can't say, I think that I am at door 1 or at door 2, because all doors are identical to the sensors. You can think of it as a likelihood or the probability of z given x. Z is the measurement. Why is the chance of being at this point, for example, x equals 50, is not 0? Because we are in a stochastic world, a world that has randomness. It is possible that the sensor of the robot is mistaken, and in fact, we are not here. We will also have a probabilistic element, and this is why Sebastian named his book Probabilistic Robotics. Now let us imagine such a thing. Our robot moved from point 10 to point 20. Now, I don't know that he moved to point 20, I just know that it moved more or less 10 meters. Now, if I know that my robot moved 10 meters, what is the new distribution look like? A moment ago, we had three peaks, and now each peak moved 10 meters right. So now we have a peak at 20, 30, and 90. Pay attention to the following thing. The new peaks are smaller. What does it mean? That the motion adds uncertainty. I command the robot to move 10 meters right, but I don't know if the robot actually moved exactly 10 meters. There are many kinds of obstacles, and it could be that the engine didn't work properly. Just remember this. A movement always adds uncertainty to the system. Now, the robot senses a door again. This is logical because if the robot was at point 10, sensed a door, moved 10 meters to the right, then it arrived to point 20 and again feels a door. So after the second sense, what is the new distribution look like? So again, if I sense the door, again I have three peaks. But now something very interesting is happening. We are in fact taking the probability when we sense the door, which is either at point 10, 20 or 80, but we multiply it, or if you like, combine it with what? With the current probabilities that we have, that the robot can be either in this point, or this point. And when I combine those two probabilities, I will get something like this. So the posterior probability tells us, after two door sense, that the most likely place or the most likely position is at x equals 20. So again, I have an indistinguishable door sensor. I cannot differ one door from the other. But if I know the map and if I can rely on past experience, I can know after only 2 iterations with very high certainty that I'm probably at x equals 20. This example encapsulates, in my opinion, the whole notion of Bayesian localization. You count on past experience and then you can gain high certainty regarding the robot position.